I actually amended the title of this presentation in honor of Travis Goodspeed. Some of you guys know him, I'm sure. So 2 years ago at ShmooCon V, Dominic Spill and I gave a presentation called Building an All-Channel Bluetooth Monitor. And I stood up in front of everybody and I said, sniffing Bluetooth is hard. And we went on to describe the success that we'd had with GNU Radio and the USRP. And I think we had some pretty interesting results. But admittedly, the solutions we presented were somewhat kludgy and required a hardware investment of $1,000 or more. As one person pointed out to us later, at the beginning of our presentation, sniffing Bluetooth was hard. And at the end of our presentation, sniffing Bluetooth was hard. So I set out to make Bluetooth sniffing easy, and this is the story of that effort. I'm going to show you Ubertooth One, which is kind of the latest fruit of my labor, and we'll talk about its capabilities and do a demonstration. But mostly today, I'm telling the story of how I got from there to here. And hopefully you'll learn some things along the way if you decide you'd like to build your own Ubertooth One, or if you're inspired to work on entirely new electronics devices. So why is Bluetooth sniffing hard? Maybe a more specific question you might be wondering is, why can't we use off-the-shelf Bluetooth adapters for monitor mode, just like we use off-the-shelf Wi-Fi adapters in monitor mode to sniff Wi-Fi networks? And you know, that would be really nice if we could, but there are some particular technical features of Bluetooth that make this difficult, if not impossible. One is that Bluetooth is a frequency hopping system, and there are 79 channels that any Bluetooth device might be transmitting on at any particular time. And different devices are transmitting on different channels at different times, and this makes it very unlikely that a passive observer is going to capture any particular packet. Another problem that's even more severe, I think, it has to do with the packet format itself. And a Bluetooth packet starts with a very short preamble of only 4 bits of alternating ones and zeros, and then the first recognizable part of a packet is an access code that is derived from the LAP, the lower address part of the Bluetooth device address. So normally when you have a Bluetooth adapter in normal use, you program that adapter to look for a particular access code or a particular address that it's looking for. And it starts monitoring, it starts receiving bits over the air, or trying to, and what it's doing is it's looking for that access code, and when it sees that access code, it says, aha, I have a packet, and it processes it. But if a foreign device is transmitting on the same channel at the time that it's listening, and it's a device that has a different address, then it'll have a different access code, and the receiver won't even recognize that a packet exists at all. It's just completely invisible to the receiver. And in every case that I know of, this correlator, this pattern matching, is implemented in silicon. Another problem, or a challenge, or a feature of Bluetooth that makes passive monitoring challenging is that packets are whitened or scrambled. Data to be transmitted are XORed with a pseudo-random sequence. And this is done for RF and electronic reasons more than it is for security, but it makes it considerably more difficult for a naive observer to decode an arbitrary Bluetooth packet that it's received. So a Bluetooth adapter would have to be specifically engineered for these solutions to these particular problems in order to enable passive monitoring. And there are solutions to these problems, and Dominic and I talked about them a couple of years ago. Josh Wright wrote a couple of Bluetooth chapters in the book Hacking Exposed Wireless, 2nd edition, which is a good book I recommend, where he described some of those techniques. But it's very unlikely that a device designed for consumer use will have been engineered with these solutions in mind, because solving these problems is a more complicated, more expensive proposition than normal Bluetooth operation, right? So if you're building a device for consumer use, why would you try to tackle this more expensive problem when you could just, when you don't have to do the things you need to do for normal Bluetooth operation? So it's been 10 years that Bluetooth has been on the market, and we still haven't, solved these problems at an affordable price. I mean, how many of you guys have ever done any kind of Wi-Fi security assessment? Anyone? Quite a few. How many of you have done any Bluetooth security assessment? Or a few? Keep your hand up if you think it was any good. Anyone? I have one halfway hand. I did that same show of hands at ShmooCon, and I think the only hand that was left in the room was Josh Wright, who wrote the book. But wouldn't it be nice if the rest of us could do that kind of work? And I know Josh would like it if he didn't have to carry around an extra 60 pounds of gear just to do thorough Bluetooth assessments. There are 1 billion Bluetooth devices manufactured on this planet every year. 1 billion. And I think we do, as security professionals, we do ourselves, our employers, our clients, and the general public a disservice by ignoring Bluetooth vulnerabilities simply because we don't have adequate tools. And I'm kind of operating on Wright's law, which is that vulnerabilities will be ignored until tools are accessible. And we've seen that in wireless technologies certainly before. We've seen vulnerabilities being exploited widely in 802.11, and we've seen the standards change and new manufactured equipment in response to those efforts. And we haven't seen that same kind of change in Bluetooth. How many of you guys were here at CanSecWest in 2004 when Ollie Whitehouse first revealed the pairing vulnerability in Bluetooth? Just a few hands up in the room, but that was 7 years ago. And since then, there have been some changes to the standards. There have been some new, more secure pairing methods, for example, that have been implemented or at least put down on paper. You know how many devices I've seen in the wild that implement any of those pairing methods? 0. Right? Every single Bluetooth device I've ever seen is still vulnerable to the attack that was discussed 7 years ago. So I think that this problem is too big to ignore, and we need better tools. And so I established a goal. I wanted to build an open source Bluetooth sniffing platform, and I wanted it to be widely available. Anybody should be able to build one of these things. I wanted it to be portable, and I wanted it to cost somewhere in the neighborhood of $100. I figured, back in the golden age of Wi-Fi hacking, like when AirSnort first came out, there was you could get a PCMCIA card that would do monitor mode for $100 or so. And so I figure if we can get into that price range, then we should be able to affect the same kind of change in Bluetooth that we've seen in Wi-Fi in the past. So I didn't know much about electronics at the time, but I knew a lot about software-defined radio. So I thought maybe I could build some kind of a special purpose software radio peripheral. And maybe it wouldn't be good for much more than Bluetooth. Maybe it wouldn't operate outside the 2.4 gigahertz band. But if I could build it out of like bits and pieces of consumer electronics, maybe I could make it really affordable. So I had this rough idea that I'd need an antenna connected to some kind of RF front end, connected to some kind of analog to digital converter, that would stuff samples over some interface to a laptop running GR Bluetooth, the code that Dominic and I wrote to work with GNU Radio and the USRP. And so I started ripping apart lots of 2.4 gigahertz consumer electronics, like cordless phones and baby monitors and video senders and wireless headsets and all sorts of things. And pretty much what I found, without exception, is that all these kinds of devices are built around wireless transceiver ICs, which are embedded in a little piece of plastic, and they're highly integrated. They have their analog sections and their digital sections stuck together in the same package. I wanted to get between those sections, and I couldn't get access to that baseband layer that I really wanted to, which was the exact same problem I had with Bluetooth chips, ICs that are built specifically for Bluetooth had the same kind of problem. So I started to get the idea that, maybe I'd have to roll my own front end somehow. And I was also looking at different options for the back end, the analog to digital converter. I looked specifically at TV tuner cards. And the most hackable TV tuner cards I was able to find were PCI cards, which wouldn't be very portable. I wanted, we're dealing with a portable technology, so it would be nice if we had portable tools to work with it. So I started to get the idea that, I'd have to maybe roll my own back end somehow too, and this was a little bit terrifying. Many of you, I'm sure, recognize this as Ohm's Law. It's a very important thing to know if you're working with electronics. And it really nicely sums up everything I knew about electronics at the time. I had never programmed a microcontroller. I had never designed a digital circuit of any kind. I had never soldered a surface mount IC. I had never designed a printed circuit board. Okay, but I can learn, and so I started trying to learn this stuff. And I think the main thing I did to learn a lot in a short amount of time is to start small. I started working on a lot of very beginner electronics projects, a lot of beginner microcontroller projects. I started reading a lot of books, talking to a lot of smart people, and trying to learn all this stuff with the ultimate goal of trying to build some kind of a Bluetooth sniffer. And along the way, I read lots and lots of data sheets. I mean, data sheet after data sheet after data sheet. And frankly, at first, I didn't really understand them. These are the essential documentation. I mean, if you're going to build electronic devices, you have to RTFM about every single part that you're going to incorporate into your device. And the way you do that is by reading data sheets. But I had to read a lot of data sheets and learn a lot about electronics, starting small, before I would even go back to the same data sheet that I'd read months before and say, oh, that's what that means. But as I was reading data sheets and working on these projects, it became clear to me that if I were to make a low-cost Bluetooth sniffer in a small package, it would have to be built around some kind of a microcontroller. And there were some microcontrollers that had embedded or built-in analog to digital converters. Hey, that might be handy. And there were some microcontrollers that had built-in USB interfaces. That could be really handy too. So I started thinking, maybe I could find a microcontroller that has a built-in ADC that's fast enough for my application. In order to demodulate Bluetooth, I needed 2 million samples per second. Well, that's pretty fast for a low-cost microcontroller, but it's not unheard of. And I also would need high-speed USB interface. I couldn't use full speed because I'd be dealing with 10 to 16-bit samples transmitted 2 million times per second, and that would exceed the limits of full-speed USB. And high-speed USB does exist on some microcontrollers, but it's also a little bit rare in low-cost chips. So it was hard to find a particular microcontroller that met both these requirements. However, the Atmel SAM3U was announced, and I thought that looked like it would at least come close. So I ordered a development board for the SAM3U, and I headed off to tour camp. Was anybody at tour camp? Yay! There are at least 2 hands up in the room. Wow! Whoa! Sorry, guys. So at tour camp, I had a great time and met a lot of great people, and that's what was so great about tour camp for me. Good times were had, and I met some really interesting people. A couple of whom actually figure into this story later on. I met Travis Goodspeed, and I'm sure many of you are familiar with his hardware hacking exploits. And I met Jared Boon, who's a similarly talented individual who designs electronic toys for a living. And both of these guys ended up, helping out with the project one way or another at a later date. And So, I got home from tour camp, and before I stop talking about Jared, the people that I camped with at tour camp were the Dorkbot PDX group. Some of you might remember Jared. If the two of you who were at tour camp, if you went and saw the electronic music performance in the Power Dome, he was one of the guys who did that performance, and I thought it was a really amazing experience. Jared also was the organizer of the Dorkbot PDX camp at tour camp. Dorkbot is a global collective of artists and hackers who do strange things with electricity, and Dorkbot PDX is the Portland Dorkbot group. A group of people from that group, came to tour camp, and that's how I met them all. And so after I got back from tour camp, I got my SAM3U development board, yay, and I started working with it. Oh no, I ran into a lot of problems, and I learned a lot, and I accomplished some important things, but there were some significant limitations. One was the ADC. The analog to digital converter is advertised as being an 8-channel, 1 megasample per second analog to digital converter. And Jared told me this would be the case, and I ignored him and had to be an idiot and figure it out for myself. But if you have an 8-channel, 1 megasample per second digital ADC, that doesn't mean that you can sample 8 channels simultaneously, all at 1 megasample per second. It means you can sample any one of 8 channels at 1 megasample per second. Okay, so this was a big problem for me because I really needed to sample 2 channels simultaneously at 1 megasample per second to try to do quadrature sampling, which is a common technique in software radio. And to make matters worse, I didn't even get 1 million samples per second on that one channel. I maxed out at about 800 kilosamples per second. And I worked with Atmel support on this, and they were very, very helpful, right up to the point where they said, sorry, you're not going to get any more than that. They said, our analog to digital converter is absolutely working at 1 million samples per second. No problem. We just can't deliver those samples to the CPU fast enough. And I was kind of disappointed in that. I felt like, okay, if their literature said 1 microsecond conversion time, and there were some additional hidden delays that I didn't know about, then I might accept the answer a little bit more. But if all their literature says 1 million samples per second, it sure would be nice to actually get 1 million samples in 1 second. These were all learning experiences, and I learned in particular here, anytime you read a data sheet and you see some maximum value and you want to operate at that maximum value, you'd better watch out. And there were some other problems with the SAM3U. One was availability. I got the development board in summer of 2009. Okay, so by March of 2010, I looked to see if I could buy an individual chip. And no, there'd be a 17-week lead time on those. So 17 weeks later, I made a note in my calendar. I went to check. 26-week lead time. Still 0 in stock. So, about 6 weeks ago, I went to check again, and it says manufacturing delays have been reported on this product. No kidding, right? So, actually, and within the last month, some of these have started to become available, but the particular model that I was hoping for is one of the ones that is still hard to come by, and it's more expensive than it was originally projected to be. So meanwhile, I was also looking at if I had this magic microcontroller that could do it all, what would I plug into the front end of it? And I was looking at integrated circuits that are designed for WiMAX and now LTE, and some TV tuner chips that were coming out that looked pretty interesting. And all of the ICs for the front end that looked like they would be most optimal for my application were new things coming out from manufacturers that they hadn't been. They weren't widely available yet, and I wasn't sure if they would become widely available. But I thought, maybe I could talk to these manufacturers and get them to send me some sample parts and maybe some documentation and figure out if I could use these parts on my own project. And so in order to approach those companies, I just kind of invented this company called Great Scott Gadgets, and I drew a little logo, and I registered a domain and put up a website and tried to make it look like I was an up-and-coming, electronics designer, a design company, and I started sending emails and getting on the phone and basically trying to social engineer my way into parts and documentation. And it didn't work at all. If you were going to pull this off, you would have to do a better job of looking like a bigger company, preferably one that actually exists and could have the purchasing power to buy like hundreds of thousands of units. I think the net result of all this effort was one piece of documentation and 0 chips. So, but what if it had worked? What if I'd gotten some sample chips for some of these parts that I wanted? What if I got some documentation? The manufacturer said, hey, sure, sign this NDA and we'll send you the specs. What good would that have done me in developing an open source project, right? So finally, after months and months of all this nonsense, I finally figured out that, gee, I maybe should have some requirements for the parts that I'm going to put on my board. One is that parts should be available. Duh. Another is that they should be available in single quantity, right? I want anybody to be able to build one of these things, so they should be able to buy the parts in single quantity. There must be public documentation available for all the parts so that people can actually understand what they're putting on their board. And you should be able to access the documentation without signing a non-disclosure agreement. Okay. So, meanwhile, I was working on more and more sophisticated small electronics and microcontroller projects, and most of them I don't even have photos of, but I do have a photo of this one. I wrote a spectrum analyzer application for the GirlTech IME, which is a $20 toy for kids to text message each other. And I was introduced to this toy by Travis Goodspeed at ShmooCon 2010, where we spent hours and hours in the hotel bar amid the terrible snowstorm, just hacking on these things. So of course, as soon as I got home, I had to order one, and I worked on this spectrum analyzer application and some related work that Travis encouraged me to work on that really got me looking at this family of wireless transceiver ICs, one of which is in the GirlTech IME. And this family of ChipCon ICs from Texas Instruments turns out is something I had looked at before. In particular, I found from months before I had notes on this CC2400, which is one of the chips in this family. But I had looked at it back when I didn't really understand what I was reading. And so I looked at it again, thanks to Travis. And it turns out it's a wireless transceiver. It operates at the 2.4 gigahertz band, which is the same band that Bluetooth uses. It supports a modulation of 1 megabit per second Gaussian frequency shift keying, which is the same modulation that Bluetooth uses. And I think the reason that I overlooked it the first time is because if you look in the data sheet, you'll see all this description of the packet format that this wireless transceiver uses. And it's somewhat flexible. You can say like different length of address field and different length of this field and, error correction on or off and some other things like that. But it was clearly incompatible with Bluetooth. But what I realized the second time around is that it has this unbuffered mode, which is a secondary interface. Basically what you do is you tell the chip to tune to a particular frequency, you activate its demodulator, and it starts streaming demodulated bits out this secondary serial interface, completely bypassing the packet handling capabilities that are on chip. And so the one thing that was incompatible with Bluetooth on this chip, I was able to completely bypass and just stream those samples into a microcontroller and do my packet handling there. Or just stream them another step along some USB and do packet handling on a USB attached PC, for example. So it turns out that this was perfect for my application, and I kind of shifted gears and went away from the software radio approach and just said, hey, I can build a device out of this thing. And so a couple weeks after ShmooCon, I was snowed in again in Boulder near my office, and I drew the Ubertooth architecture for the first time, and it's pretty much the same today. It's an antenna connected to a CC2400 wireless transceiver connected to a microcontroller with a full-speed USB interface to a PC. I didn't have to use high-speed USB anymore because I'm not dealing with raw radio samples. I'm dealing with demodulated bits at 1 million bits per second. And I can fit that over full-speed USB, which gives me a lot more flexibility on what I do in the back end. Now, Jared Boon, who I mentioned earlier, was also interested in the CC2400, and he was kind enough to design a little breakout board for this chip. And he had some made in the Dorkbot PDX PCB order, which is, has anybody here had anything done by the Dorkbot PDX PCB order? No? Well, it's a great resource if you ever design printed circuit boards or you think you might want to try it in the future. There's a guy named Lane who's a part of the Dorkbot PDX group, and he collects designs for small boards from a lot of people all over the world and panelizes them all together and gets them made as a group in order to get really low-cost prototype boards for people. And so Jared had some made through this service, and I got a couple, and I got it working by connecting it to a GoodFET at first, which is a board I got from Travis, Goodspeed. And then I started connecting it to other microcontrollers with more sophisticated USB connectivity, and ultimately settled on the LPC 1700, which is an ARM Cortex M3 processor from NXP. And I got a little development board for the ARM for that LPC 1700. I connected it to Jared's breakout board and connected the USB to a PC, and actually kind of got the Ubertooth architecture working for the first time and decoded my first Bluetooth packets with it, which was very exciting. And based on that success, I designed a board that would do all this in one package that was called Ubertooth Zero, and I had some made just in time for TourCon last fall. And I actually was able to get some made and give them away at TourCon, and that was all very exciting, but I knew that it was kind of a stepping stone. It was my first circuit board in this project, and I knew I wanted to make an Ubertooth One. So Ubertooth One started right after TourCon, and I wanted to get it. I wanted to have it finished and working by ShmooCon, which is just like 3 months later. So I was hoping to have my first prototype working by the end of November, and well, that didn't happen. And I was hoping to have it working by the end of December, and that didn't happen. And I have all kinds of excuses why this didn't happen, because I had some bad boards produced due to a file format compatibility, and I missed a deadline due to my own injuries. And word of advice: if you ever see a car starting to roll down a hill without a driver, and you think to yourself, I could chase down that car, jump in, and stop it. Just don't. So for a variety of reasons, I didn't get this thing done until 3 days before ShmooCon, and I did actually have working boards at ShmooCon, a couple to give away, and that was all great. And the main thing that's different about the Ubertooth One compared to the Ubertooth Zero, the only real functional difference, is that it includes the CC2591, which is an extra little chip that's an amplifier. It improves both the transmit power and the receive sensitivity. It basically turns it from a Class 3 Bluetooth device into a Class 1 Bluetooth device, which is a lot more useful. So, and the CC2591 has a 4-layer circuit board in its reference design. And I had never designed a 4-layer circuit board before, and I tried to adapt it to a 2 layers, and it didn't look like it was going to work very well. So I looked into what I'd have to do to design a 4-layer board. And I had designed Ubertooth Zero in EagleCAD, which is pretty good software, but it's crippleware. I would have had to pay a licensing fee to unlock the 4-layer capability. And I thought, well, it really wasn't that expensive. I thought, maybe I'll go ahead and do that. But then I thought, how lame would it be to have an open source hardware design that people couldn't modify without paying a license fee for some software? So I decided to give GeekOut a try, and I'm really glad I did. It's an excellent piece of software. It's fully open source. It did everything I needed to do, and I was able to design a 4-layer Ubertooth One with it, and now I'm using it for all my projects. So the Ubertooth One looks like this. It has an antenna connector, a CC2591 amplifier, a CC2400 wireless transceiver, and it's all controlled by an LPC 1700 microcontroller with a full-speed USB interface. And you can really use, if you build one of these, you can use any of these microcontrollers from the LPC 1750 family. They're all pin compatible with each other, and they really don't have much difference other than what's listed in this table. Personally, I have yet to build any firmware that exceeds 32 kilobytes at this point. But I can imagine in the future having bigger firmware. And so I'm considering as a kind of the basic Ubertooth model that it should have 128K of flash for program memory. The board I'm demonstrating today has 512K, but I'm not really using any of that at this point. So let me do a little demonstration. I actually fired up Kismet before my talk, and it's still going. So I wrote a little plug-in for Kismet to talk to Ubertooth, and as you can see, it's collecting packets from things. One thing to note in particular here is that the address that you see the most of, at the very bottom, 9E8B33, that's actually a universally used address that is used for inquiry when you're trying to locate a discoverable device. That's actually the general inquiry device address. So it's one that we see very often when we do this kind of thing. But we can also see that there's been quite a bit of other Bluetooth traffic in the room. And oh, and there's another device. So that's pretty much my demo. I have some command line tools to work with the Ubertooth, but I figure that kind of the main user interface that most people will use most of the time if they're not developing their own firmware, it would be Kismet, because it's really, really easy to use. Yay, surface mount technology! When I started this project, or early on in this project, I saw some really impressive surface mount soldering demonstrated by people like Travis Goodspeed and Amanda Wozniak and the SparkFun guys, and I thought, wow, I want nothing to do with that. And then, gradually over many months, I kind of came around to the idea that it would be a necessary evil. But ultimately, I learned to love it. Seriously. Surface mount technology, surface mount parts are small, they're cheap, and they're fast. And I don't just mean they're fast to assemble, I mean they operate with higher frequency electrical signals. They can do things that their older, larger counterparts with longer leads could not do. It wouldn't be possible to build a little USB dongle for Bluetooth sniffing without surface mount technology. And it's really not that hard to work with if you do it like this. First, you have custom PCBs made. Don't try to use surface mount parts without having custom PCBs made. And you can get them made very affordably, even 4-layer boards, which a lot of people don't realize. A lot of people who have done home electronics projects have really been limited to 2 layers, but you can, through Lane's order at DorkBot PDX, for example, you can get a 4-layer board. In fact, you can take the Ubertooth One design and send it to them and get 3 copies of it made for $18, which I think is a pretty darn good deal. And you should also get a stencil. I've tried applying solder in other ways to the board, but I highly recommend using a stencil. It's way, way, way easier than any other option. All you do is you get some solder paste, and you get a stencil, and you hold it on the board, and you smear the paste over it, and lift the stencil, and you're done. So you can get a stencil made of Kapton or Mylar. This is a Kapton one for about $25, and that's pretty affordable, I think, especially since you can use it several times. And there are potentially even lower cost options. And I'll mention Jared Boon again. A few weeks ago, he posted on his blog a fairly successful experiment where he just took some Avery labels, just some adhesive labels that are made for printing at home, and stuck them in a laser cutter and made his own stencils that were adhesive. Why bother paying for an expensive material like Kapton when you're only going to use the stencil once or maybe 3 times? You can probably get 3 Avery labels for less than the cost of a single Kapton stencil. I tried the same thing and I had slightly worse results. I had a friend in Colorado with a laser cutter, and he was kind of interested in maybe making a low-cost single-use stencil service available to people. And we tried Avery labels, and you might be able to see in that picture there's some white stuff stuck to the circuit board. This is after I've applied the solder paste and I'm peeling the stencil away. Some of the adhesive stayed there. My adhesive was stronger than Jared's was. So I didn't have as good success, but this is definitely an area that's worth further trials. I'd like to try post-it craft paper, for example, instead of Avery labels and some other materials, and see if we can find a cheaper solution. But however you manage to get your solder paste stenciled onto the board, then you just place components. You'll need a fine tip pair of tweezers, like tweezers you can get at SparkFun for like $4 or something. This isn't as hard as you might think, even though these components are quite small. The solder paste on those pads makes them a little bit sticky, and that helps a lot. And you just kind of, focus in, and everything around you starts to look really large. And pretty soon you have all of the components on the board, and you just put it in an electric skillet and heat it up until all the solder flows, and turn it off, and you're done. You should get one of these infrared thermometers. You don't really need it, they're just fun to play with. And thanks to surface mount technology, I was able to make this device small enough to fit into an off-the-shelf enclosure. You can buy this little black box online for like $3. And personally, I prefer just to put a little bit of transparent heat shrink tubing around the board, because that protects it adequately in my experience, and it also allows you to see the pretty blinking lights. But if you want your board to look like something that you bought at Best Buy instead of something that you won in a poker game at a HackerCon, then you can do that. So what's the total cost of this thing? The bill of materials, all the parts that are soldered onto the board, add up to about $40, a little under. You can get circuit boards made, 3 for $18. You can get a stencil that's good for probably a few dozen uses for $25. You probably want an antenna, and you might want an enclosure, and all together, not counting extra parts you'll need when you screw things up, not counting solder and tools like your tweezers and your electric skillet that you might have from other projects, and not counting a few miscellaneous shipping charges, the total is under $100, which is what I was aiming for in the first place, and that's even if you only want to build one board. Of course, it costs reduce if you build a few. And what can it do? What I was demonstrating with Kismet is just Bluetooth basic rate monitoring. And this is such an important function. I mean, some of you, I'm sure, have experimented with Bluetooth hacking in the past, and we actually have some pretty interesting tools out there. That there's one essential tool that has been missing for all these years, and that's the ability to passively monitor and discover non-discoverable devices. Right? All you guys know, I'm sure, that you should not have your Bluetooth devices in discoverable mode. Right? You turn that off. But it's totally possible to sniff passively Bluetooth traffic and determine their device addresses without them being in discoverable mode. And we've never had that tool available to us at a low cost. And that's the main thing, the killer app of this device that really makes it useful. Because it opens the door to so many techniques that we already know about, and probably many techniques that we don't know about yet, just by virtue of being able to passively detect devices and find out what their addresses are. So that's huge. But it's based on a wireless transceiver. It both transmits and receives. So we should be able to do Bluetooth injection with this thing. Of course, I don't have a lick of firmware that does that yet, but it's a capability of the hardware. And in addition to doing Bluetooth basic rate, which is the kind of stuff that all our Bluetooth devices to date pretty much use, there's also a new technology called Bluetooth low energy, which is a completely new physical layer standard that is just coming out now. Consumer devices will probably arrive sometime later this year, and we'll be able to use Ubertooth to monitor and inject that. We can use it for some other technologies and for some basic spectrum monitoring. Just a couple weeks ago, I implemented kind of a simple spectrum analysis function using the Ubertooth. And so here you can see, like on the left is a big, busy, noisy Wi-Fi channel. And then there are some other little spikes throughout that are Bluetooth traffic. And this is a kind of a proof of concept. The first packets that I intercepted from a Bluetooth low energy device. So I haven't gotten very far with that, but it demonstrated the capability. And so overall, I think it has really important capabilities that we've been needing to have at a lower cost. And I've been accused of plagiarizing this slide from Gartner Research, but I promise I drew it myself. From the very beginning, the goal of this project was to get this technology into the hands of more people. And number one, that means it had to be open source. I absolutely wanted to make an open source device for everybody. But I also wanted to make devices, eventually it sort of dawned on me that people would actually want to buy this thing. And I said, well, hey, I have a company. And maybe I should just build these things and sell them and pretend my company was legit all along. And so I did that. And over the last few weeks, I had a run on Kickstarter.com that I know many of you pledged your support for, and I thank you very much. Kickstarter is kind of a crowdfunding site, and essentially in this case, it's a trusted third party to take pre-orders. I established a pledge goal, and we blew away that goal by like 300%. So thanks everybody who did contribute. Because of you, I am getting a run of boards built, and that they'll be in production very soon now. And once I get all those boards delivered to the people who pledged, then there will also be some boards available through some online retailers that hopefully they're okay with me telling you their names, because this is all very preliminary at this point. But Sharebrain Technology is a small company that's actually owned by Boon, who I've mentioned several times today. He not only helped with this project in helping me along the way at many steps, but he also sells his own open source hardware designs at his website, and he's going to carry Ubertooth. Hack5, I'm sure many of you are familiar with. They have their video series, and then they also have a little store where you can buy things like their Wi-Fi Pineapple. And SparkFun has a tremendous resource for hardware hackers. And all these guys, it looks like, are going to be carrying Ubertooth after the Kickstarter era. So I want to say big thanks to a whole bunch of people. Obviously, I could not have accomplished what I did in 2 years without the help of a lot of people. And I want to call out in particular Dominic and Jared. Dominic Spill, really, he and I worked on together, and he worked on before me, the GR Bluetooth project, which is a GNU radio implementation for Bluetooth. And it was that work that really that really demonstrated that this whole thing might be possible in the first place. And Jared, who I've mentioned several times, really has been a mentor to me and has helped me through all my stages of learning about electronics. And everybody listed here really had some kind of a strong impact on this project. I want to point out before I go some related work. The Killer Bee project from Josh Wright is kind of a similar tool for Zigbee. He didn't have to design and build his own board because he found a development board that met his needs. So, but it's the same kind of tool with similar kinds of functions for Zigbee networks. The Kikiriki project, didn't these guys present last year here? Thorsten and Max? Yeah. Their version 1 was a sniffer for 27 megahertz wireless keyboards, but their V2 targets 2.4 gigahertz wireless keyboards that are non-Bluetooth, they're proprietary 2.4 gigahertz. And they had a lot of the same challenges that I did and come up with some similar solutions too. But it's a really interesting open source hardware project for wireless communication security research. And the Next Hope badge that was designed by Travis Goodspeed, if you haven't seen his, I think, most recent blog post, it was just a few weeks ago, he showed how he could use the wireless transceiver on the Next Hope badge, and that this badge was a variant of his GoodFET project with a wireless transceiver tacked onto it. He was able to target some of the same things that the Kikeriki V2 did, at a lower cost and using some really clever techniques. And all of this stuff really is exciting to me. It's exciting to be a part of this community that's kind of bridging the gap between the InfoSec hackers and the hardware hackers, and designing open source hardware to do this wireless security research. And it gives me a lot of hope for the future. In the future, when there's a popular new standard for wireless communications, we aren't going to wait around for 10 years for somebody to build hardware for us. We'll just build it ourselves. So thanks for listening.